Hi, Stuart.
Hey, Bob.
How you doing?
Very well. How are you?
I'm doing fine. Let me introduce us. I'm Robert Wright. This is The Wright Show, available both via streaming video and as an audio podcast. You are Stuart Hameroff. You are at the University of Arizona. You're a professor of anesthesiology and psychology, I believe. You're very well known for a couple of things. For one thing, you founded a conference that's now kind of famous that happens every year, and every other year it's there in Tucson where you are. A conference that's devoted to studying consciousness and did a lot to, I think, kind of put the field of consciousness studies on the map and give it a kind of coherence. It's a medium by which people got to know each other who are researching this and so on. So it's very well known. Actually, it's lately taken some heat for being a little too, in some respects, woo. There was a piece in the Chronicle of Higher Education by a journalist about that recently, and we'll talk about that, whether you're too woo, or whether you allow overly wooish people to attend your conference. But the other thing you're well known for is you actually have a theory of consciousness that you developed with Roger Penrose, the eminent mathematical physicist who I guess is taught at both Cambridge and Oxford. And so that's what I want to start out talking about. We'll talk about your theory, and then we'll eventually get back to the conference itself. Now, one thing, maybe the way to start any conversation about any theory of consciousness is to use a phrase that actually was kind of launched at your first conference. The phrase is the hard problem of consciousness. It's associated with David Chalmers, who was at the first conference in 1994, I think. Then he wrote a book called The Conscious Mind that came out a couple of years later. I'm sure it was in progress when he was using the phrase at the conference. But what does that phrase mean to you, the hard problem of consciousness?
It means experience, awareness, conscious, phenomenal perception, as opposed to behavior or learning, memory to some extent, other brain functions that could be done without consciousness, or that could be done by a computer or a robot without having any inner life, any inner experience. And Dave ticked off a bunch of easy problems like learning, memory, attention, reportability, and so forth, and said those are all relatively easy. Of course, they're difficult problems. But the really hard problem, he said, is why we have awareness, why we have experience, why we have subjectivity, a first-person point of view. Now, other people had said it differently going back to ancient times. More recently, Tom Nagel, What Is It Like to Be a Bat? John Searle with distinguishing consciousness from behavior with his Chinese room experiment, and so forth. So Dave elucidated the hard problem to distinguish it from other brain functions. And I think that's a distinction and an issue that still goes forward, because a lot of neuroscientists and cognitive scientists are working on relatively easy problems and think that's all there is to it, and that consciousness will just come out of the mix in some way. But Dave said, no, it's a separate issue. It may or may not come out of the mix. Let's see. And he set that forth in 1994. I should add that when I organized that conference, I had some co-organizers, but the approach we took was a week-long conference. The first day was philosophy, the second day was neuroscience, the third day was cognitive science, psychology, the fourth day was mathematics and physics, the fifth day was phenomenal experientialism. And the first morning, the first two speakers were very well-known philosophers. And the third speaker was Dave, who had submitted an abstract. He was unknown at that time. And he kind of lobbied me by email to give him a plenary spot. And I did. I thought his abstract was interesting. And it was a good thing, because the first two speakers literally read their talk without any slides. And the interdisciplinary crowd, not used to that, was literally dozing and falling asleep. So we got off to a very slow start. Dave got up and pranced around, and he kind of had a rock star manner and started talking about the hard problem, and it kind of caught on. And at the coffee break, after people were talking about the hard problem, and that's kind of why we're here. And that moment really galvanized the field. helped make that conference a success and helped launch the conference series and the modern movement, interest in consciousness studies and science.
You mentioned a few formulations of the hard problem. I personally do like one you alluded to, Thomas Nagel's. Just, you know, it is the mystery of why it is like something to be alive. Why aren't we just the machines without the interior experience? So your theory and Penrose's theory invokes quantum physics to explain consciousness, and I think what I'm going to do is try to lay out what strikes me as distinctive, or at least one very distinctive thing about it, and give people a little bit of background in quantum physics, and then I'll let you correct me if I'm wrong or fine tune what I said, and then we can kind of launch into it. But as a lot of people I'm sure know, quantum physics is weird. One thing it says is that there are times when, like, if you ask the question, where is this electron, there's no simple answer. I mean, the answer might come in the form of, well, there's a 20% chance it's here, 30% chance it's here, 50% chance it's here. And if you say, well, what does that mean? Depending on the interpretation that the particular physicist or philosopher has, they might say, well, it means the electron's really not in any of those places. Or they might say, it means it's actually in all of those places. But whatever they say, what they agree on is that there's no single answer to the question until you measure it. Once you measure it, then you can say, okay, it's right here at the actual moment of measurement, leaving aside the question of what its fuzzy state was right before that. Now, there have been various ways of interpreting quantum physics, and in particular, answering the question of, well, wait, why does it assume why is there suddenly a distinct answer to the question when you measure it, whereas you're sure that there wouldn't have been if you hadn't taken the measurement? And there have been a couple of explanations. One is that, well, there's something about the way the electron just interacts with the physical measuring device. Another, more exotic one has been, well, actually, it's not the measuring device. It's the act of observing. It's the person there overseeing the measurement. It's actually the person's, in some sense, the person's consciousness, the person's subjective experience, the act of witnessing that forces it to come, the electron to assume a definite location. And that, of course, is pretty weird. But what's interesting about Penrose's theory, and subsequently, you and he collaborated to develop a more specific version of it, is that he's saying, no, it isn't that consciousness makes the wave collapse, as they say. This is the term. They say that before you measure it, the electron is in superposition. It can be described as a wave, maybe a probability wave, but it's in superposition, and then the wave collapses upon measurement. And what Penrose said was, it isn't that consciousness makes the wave collapse, it's that the collapse of the wave creates the consciousness, right?
Yes.
That's interesting, and it's I guess in my mind a kind of, and we should say, I mean, just to give a little foreshadowing, what you brought to this is specific ideas about where in the brain quantum processes could plausibly take place. You put a lot of emphasis on these things, microtubules, which are inside the neurons, and you emphasize intraneuronal activity, in a certain sense, maybe more than interneuronal activity for purposes of explaining consciousness. But in any event, I guess the question that springs to my mind, for starters, is, well, then what is making the wave collapse? I guess perhaps naively, I'm looking for like the source of the consciousness, right?
Let me go back. You covered a lot of area there. First of all, how is something, a particle in multiple locations or acting like a wave, so it's not just here, it's here, 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 and here. That's called quantum superposition. Mm-hmm. And it means that something can be both here and here at the same time. You can think of it as a wave, or you can think of it as just being in two places at the same time. And it's true that back in the early days of quantum mechanics, Niels Bohr and others doing quantum experiments found that a system could be in superposition, but when they made a measurement with a measuring device and looked at the measurement, it would choose one or the other. And initially they thought, well, it's the measuring device. And then Wigner and von Neumann and others figured out that it was indistinguishable to say the measuring device caused it or the conscious observation of the results in the measuring device caused the collapse, such that the results could be in superposition while in the machine until somebody looked at it. So that's called the Copenhagen interpretation, because Niels Bohr was Danish, and he kind of started it.
Now just to be clear, I mean, the Copenhagen interpretation doesn't say that consciousness makes the wave collapse, right? I mean, isn't the Copenhagen interpretation kind of an agreement not to get too specific about what the interpretation is, or am I wrong?
Well, that's basically right, that the measurement causes it, and in some way, and Bohr wanted not to have to worry about the underlying nature of reality.
Right.
And he argued or differed with Einstein, who was really concerned about what was going on, how something could be in two places at the same time. But Bohr wanted to do measurements, and the famous quote was, "Shut up and calculate, just keep doing without worrying about what's going on." And so the general area became known to a lot of people as the Copenhagen interpretation, that conscious observation causes collapse. And that's still one of the popular views. The other, another popular view is that if you have a particle in two places at the same time, that they don't collapse. Each one evolves its own universe, continues and evolves its own universe. So you have multiple worlds, multiple overlapping universes. And despite the absurdity of that, it's a very popular opinion among physicists, because the mathematics work and they don't have to worry about the nature of superposition. They don't have to worry about consciousness. They certainly don't want to think about consciousness. And it's a very popular view of multiple worlds. Then there's decoherence, which basically says superpositions that run into classical states will get drowned out and lost in the noise and basically go away. That's not really a solution. There's a bunch of others, but Roger Penrose turned the consciousness causes collapse 180 degrees in reverse, and as you said, that collapse causes or is consciousness. And if you say collapse causes consciousness, then, as I've learned, Dave Chalmers or philosophers will say, well, then a lot of things cause consciousness. Breathing causes consciousness. Blood flow causes consciousness.
Wait, why do they say that? I mean,
well, without breathing, or I mean, I'm being a little bit ridiculous.
Well, yeah, of course. If we weren't alive, we wouldn't be conscious. But you and Penrose are making a much more specific claim that
we're making an identity claim. And when I said I objected to Dave's argument, he said, well, then are you making an identity claim? Which means that collapse is the same as consciousness. Collapse is consciousness. And having to choose between those two, I said, okay, identity theory, collapse is consciousness. And but that raises your question, well, why does the collapse occur? And the answer to that is Roger's brilliant insight, which I'm sure Einstein would have loved because it's right up his alley. And what he did in doing that was bring in general relativity. And Einstein's general relativity, as you know, deals with space-time curvature. And Einstein said, and this argument goes back to the Greeks, are objects moving in a void, or are objects embedded in some metric or plenum, as the Greeks called it, or ether or something in which everything is embedded? And Einstein came up with a space-time metric and said that matter, causes or is equivalent to curvature in this space-time geometry. And he said, for example, he predicted that light from a star behind the sun the starlight would be bent by the mass of the sun and would be visible if you weren't blinded by the sun, even when it was directly behind the sun. And so in 1929, I think it was, Eddington went to a mountaintop during an eclipse and observed that stars which were known to be behind the sun were visible by exactly the amount predicted by Einstein's general relativity due to curvature. So Roger Penrose took that idea but applied it not to just big objects like the mass of the sun, but to very tiny quantum particles like an electron or a proton or something like that, which if it's over here is a little tiny curvature in this direction, say if it's over here is a little tiny curvature in this direction, and therefore superposition, the particle in both places would be simultaneous curvatures here and here. So the structure of space-time geometry, and we don't really know what that is, although Roger's probably the world's expert on this, actually separates because of opposing curvatures, and there's a blister or a bubble in the fine scale structure of the universe. Now, you could imagine if each of these curvatures possibilities continued, if it's a separation in space-time geometry, and if they stayed separated and evolved, then you would get 2 universes, and then 4, and then 8 multiple worlds. So this is also the beginning of the multiple worlds hypothesis, that space-time geometry separates due to curvature with each particle. But Roger said that the separations would be unstable. And you might have a little tiny blister, but it's not going to shred the whole universe. It's not going to separate because they're unstable. And after a time t, given by a very simple equation, the indeterminacy principle or the quantum uncertainty principle, pretty much the same thing, where E equals h over t, where E is the gravitational self-energy, the amount of separation, the amount of mass separated from itself, or the amount of space-time separated from itself, equals h bar, Planck's constant, over 2 pi, over the time at which objective reduction or collapse will occur.
Okay, so he's saying that there are just certain circumstances where the continued existence of these 2 particles as 2 particles, or as more than one particle simultaneously, is unstable. The laws of physics just force collapse when certain things are true of the system, when certain measurements would hold.
Right. It's a property of space-time geometry. It doesn't want to be torn apart. You could think of it as elasticity or something, or annealing or something like that. Roger doesn't like those terms, but the separation is unstable and will collapse to one or the other at a time t. The larger the collapse, the smaller the t, the quicker the collapse will occur.
I mean, that still leaves me kind of wondering I mean, it seems in a way an unsatisfactory answer, because I guess I still am wanting something in the computing machine to be the source of consciousness. And this almost sounds as if it's something outside of the machine. And maybe we should back up and revisit this book that Roger Penrose wrote that was very, very famous at the time, The Emperor's New Mind, which was a critique of artificial intelligence, because this feeds into his theory, I think, of consciousness. And what he said was, he used Gödel's incompleteness theorem to argue that all of these artificial intelligence people who were contending that we could arrive at a complete, simulation of human understanding via machine, via computation, were wrong, because according to Penrose's interpretation of Gödel's incompleteness theorem, if I've got the name right, the name of the theorem right, according to Penrose's interpretation, a computational system cannot within itself generate true understanding, right? And he associates understanding with consciousness. So we should say that according to this argument, in a certain sense, the consciousness and understanding have to originate in some sense outside the system. Now, we don't mean spatially outside it, because the microtubules, where you see the quantum effects happening, are inside the neurons. But I mean, outside of the deterministic computational system, or what? Is that the way he would put it?
Yeah, something outside the computational system. And what could that be? And that's where he seemed to go to pull something out of left field and say the non-computable effect was having to do with quantum physics, and was also a solution to the measurement problem in quantum mechanics. So let me back up a second. He started with mathematics and said to prove a theorem, the theorem can't prove itself. You have to be outside to judge whether it's true or not.
That's Gödel's idea.
That's Gödel's theorem, right. And John Searle had a very similar argument called the Chinese room argument, where he said, imagine a person is sitting in a room, doesn't speak a word of Chinese. He's handed a series of Chinese letters or words, whatever you call them, and a lookup table. And he looks at the symbol, ideogram, or whatever you call it, looks up the table and said, oh, it means this, writes it down, next one, next one, next one. At the end of the day, he's translated something from Chinese into English, but he doesn't understand Chinese. He doesn't understand Chinese. That's very much what Roger was saying, that we don't, machines don't understand. They can do tremendous calculations, tremendous computation, give us amazing results, but they don't understand a damn thing. We do the understanding.
And by the same token, he would say these machines aren't conscious. Because, I mean, some people in consciousness studies will say, well, we don't know. For all we know, my computer does have subjective experience. But I gather Penrose would say, well, no, we understand that this is just a straightforward computational system, so it can't be conscious.
That's correct. However, he also says that these objective reductions, these self-collapses, and basically, let me just explain, quantum state reduction due to an objective threshold, the objective threshold being E equals h over t, as I just said, gives you an objective threshold. So this self-collapse he called objective reduction, or OR, objective reduction. So he was saying that when that occurs, the system will reduce to one state or the other, and that could be occurring everywhere in the environment, in the table, in the air, in other cells outside your brain, in molecules, in inert objects, all over the place, all the time. Now, that seems very weird until you consider that leading neuroscientists like Christoph Koch and Giulio Tononi have resorted to panpsychism because they've given up on trying to explain consciousness.
Right. Panpsychism is the idea that all physical things have at least some tiny increment of subjective interiority or something, so the consciousness, in a sense, pervades the universe, although not in this complex form that we enjoy. And so you're saying an implication of Penrose's theory would be that, yeah, since these objective reductions happen in coffee tables, there might be a tiny degree, an increment of sentience, subjective experience in the coffee table.
Yes, he called those types of objective reductions proto-conscious because they're not connected. There's no meaning. There's no memory. They come and they go. There's no consequence. They're happening all the time. The point is that, as bizarre as that may seem, it's less bizarre than panpsychism, which says that consciousness is a property of all matter, of all atoms. And the problem with that is that there's several problems. Number one is, how do you combine those individual consciousnesses in the brain to our consciousness? Mm-hmm. And we have the same problem with objective reduction, but I'll come back to that. And also that these atoms or these small particles are not really particles at any one time. They're going in and out of superposition. So they become, the atom smears out and then collapses to one or the other. So to be a panpsychist at that level, I think you can't ignore quantum mechanics, even though panpsychists do that. So I think Roger's objective reduction is much better than panpsychism because it takes the quantum nature of particles seriously, and number two, can be combined into the kind of consciousness we have much more readily, through our theory anyway, through microtubule orchestration, than panpsychists can combine their individual atoms into the kind of consciousness we have.
Okay, so in this view, consciousness and understanding are in a certain sense imparted. I'm sure he'd say, yeah, the brain does a certain amount of computation, right? It's just that if you ask, like, what gets us over the edge to true understanding and consciousness and awareness of our understanding and so on, that comes from outside the computational system. It comes from the physical universe, I guess he would say, in accordance with physical laws, but outside of the computational system.
Right. So you can imagine that the brain is a computer and neurons and synapses do computation.
Right.
Although I'm not 100% that's true. I think it's a little bit different. But let's say that's true. You can also think of microtubules, which we haven't talked about yet, as being quantum computers, and they evolve quantum information by the Schrodinger equation, and then reach this threshold and collapse to the answer, one or the other, or one of many possibilities. And the other thing that Roger added in that book is that in the objective reduction process, the choice of, say, here, or this perception or that perception, or this action or that action, is not random, as it is in Copenhagen or observer-induced or decoherence or even multiple worlds, but rather is influenced by what he called Platonic values embedded in the fine-scale structure of the universe. And this doesn't necessarily mean the universe, out there, because there's space-time geometry everywhere, including within our brains, in and around our microtubules. I mean, you can think of everything as curvatures in space-time geometry. So
maybe we should pause here on the word Platonic, just for refresher course for those of us who haven't had a philosophy course in a long time. So Platonic, there's an argument among mathematicians, like, or at least philosophers of math, like, are mathematical truths like real, and are numbers like these real things that are like universal and in some sense out there, or is the language of math almost just like a game of chess? It's a system, we invented these rules, and it works, but it's not, Plato, of course, had this idea of like the forms, this world where there's like an ideal version of a chair, and all the chairs we see are just kind of variants of the Platonic ideal of a chair. And correspondingly in math, some people would say, yeah, in a similar sense, numbers and mathematical concepts and so on are out there, so to speak, and we discover them, but they were already out there, right? Now, I want to say one interesting thing I happened upon during the just over the last few days was that Gödel himself was a Platonist, and that was actually a motivation for him to look into, to formulate the incompleteness theorem, because he wanted to explain to these like mathematicians that if they thought they had created some little like game of numbers that was really solid, they were wrong. It couldn't be really solid if it was just like an invented. I'm sure I've already said something wrong, but it is interesting to me that Penrose uses Gödel's incompleteness theorem and is a Platonist, and Gödel himself was motivated by Platonism to develop the theorem. Now, with that having been said, I'll give you one or two options. You can either correct something I said, or can you shed a little more light on what you mean specifically when you say that Roger is a Platonist? I mean, how that really relates to his theory of consciousness or his interpretation of quantum physics?
I would say that he's a Platonic realist. Plato's ideas are usually taken as abstract forms. Roger would say, I believe, and I'm not 100% sure he'd agree with this, but I think so, that these Platonic values are embedded in the fine-scale structure of the universe, and that when the collapse occurs or the objective reduction occurs, there's a bias. There's a bias towards one solution or the other, or one of many, because it's influenced by these Platonic values. Now, I think of it in the following way, and I'm not 100% sure Roger would agree with this, but I think of it as saying the solution that is chosen, that is influenced, pushed towards by these Platonic values, do so because they resonate with the fine-scale structure of the universe, whatever it is. Now, when you get down to the Planck scale, we don't really know what the universe is made of. Nobody knows. Roger's probably the world's expert on that. Spin networks, twistor theory, some people say strings, but strings don't have they still need a background, so they don't really help. So whatever it is, when you get down to the Planck scale, things have information, things have irregularity, and that's where the Platonic information is embedded. And it could be that the influence, Platonic influence, is because that particular selection resonates with the fine-scale structure of the universe.
Okay. Now I want to get into microtubules because that's where your contribution to the theory comes in. But first, one more question. Is this a deterministic? Well, I mean, I guess if it involves quantum physics in some sense, it can't be. Well, but what I mean to say is, do you and/or Penrose believe in free will?
That's a bit of a complicated question. There are several problems with free will. Determinism is one. Is everything already predetermined and we're just following, a path and have an illusion of making choices? But the other is a much more basic problem in neuroscience, which is to say that, let's say you and I are talking at a cocktail party or even online, and you ask a question and I answer immediately. And if someone were to be looking at my brain for the activity of what you said, it would occur after I've already responded. This is a well-known issue in neuroscience and cognitive science, been known for many, many decades. The mainstream view, started by Dan Dennett, Dan Wegner, and taken by most neuroscientists now, is that I would answer you non-consciously, my inner zombie, my inner robot, whatever you want to call it, autopilot, And then a fraction of a second later, I have this false illusion that I answered consciously. So I think I'm in control, but I'm not. That's the party line in neuroscience and cognitive science, that consciousness is epiphenomenal. It doesn't actually take part in choosing.
Right. So an epiphenomenon is something that is influenced by, in this case, you would say maybe the physical world, but does not in turn influence it. It's just like what the shadow of my hand is to my hand. In this view, consciousness is just a kind of a shadow that's cast, and according to the experiment you describe, it's cast after the actual action has taken place. And this is, I wasn't really aware of this, I guess, but what you're saying is that the finding is that you say something to me, I reply, and I kind of imagine that I'm consciously formulating the answer, at least that's what it feels like, but you're saying that actually the parts of the brain associated with my conscious awareness of the whole thing don't kick into gear until after I've already responded. Is that right?
Your conscious perception of the stimulus, of what I said, happens. The brain activity happens after you've responded. So what the so-called experts say is you responded non-consciously and subsequently have a false illusion of having answered consciously. As T.H. Huxley said, we are merely helpless spectators along for the ride. Your inner autopilot, inner zombie answer. Now, there's a lot of problems with that. Number one is, where is the electrical activity occurring with the automatic inner zombie response? In other words, if you're answering non-consciously, there should be some activity there, and we don't see it. It comes later. So it's problematic to begin with. Now, Ben Libet, a very famous neuroscientist in the late 70s, an amazing experiment on patients in neurosurgery awake. They had, under local anesthesia, holes in their skin, scalp down to the brain, and he was able to access, for example, the sensory part in the sensory cortex for, let's say, this finger. And he had this patient awake. He would stimulate the finger and record from the brain, or he could stimulate the brain and, in both cases, ask the patient, when did they feel it? And he had a very clever way of having them tell, because just the act of saying now takes some time. And you would expect, I think most people would expect, that stimulating the brain directly, you'd get an immediate response, and stimulating the finger would be delayed because it takes time to get to the brain. And in fact, when you stimulate the finger, it takes about 30 to 90 milliseconds to get a sensory evoked potential, and that's when you feel it. But what he found, and if you stimulated the brain, he found directly, he found that it took 500 milliseconds to have a sensory experience of the finger. So he's stimulating the finger point of the brain. Half a second later, you say, oh, I feel it in my finger. And so there was a delay. Now, he then did other experiments that are a bit complicated, but basically if you stimulate, you can get an evoked potential, but then stop the stimulation, and there's no sensory perception. It turns out that the brain knows, or somebody knows, or consciousness knows, depending on how you want to put it, that you get the evoked potential, and then you're going to have another 300 to 400 milliseconds of brain activity. And if that occurs, you have the conscious experience, but you have it at the time of the evoked potential. Therefore, the brain knows what's going to happen in the near future. And he called that backward time referral of subjective conscious information backward in time.
So now we're getting pretty weird. Now, of course, we should say that physics... What's that?
This is perfectly okay in quantum physics.
I mean, physics does leave open the possibility of things moving backward in time. Still, I think weird is a fair term, even if the laws of physics...
well, consciousness is weird.
Yeah, exactly. Consciousness is weird. And I'm not sure, for all that has been discussed, I'm not sure people adequately appreciate how weird it is. The point quickly, what's that?
I was going to say that in Emperor's New Mind, Roger discussed Libet's 500 millisecond delay and the anomaly, and said there must be some kind of backward time referral. And he mentioned his own ideas on temporal non-locality, and also Aharonov's dual vector theory. And there's many examples in physics of time symmetry. And it seems like, quantum information can go backwards in time, and may be necessary in entanglement where you have non-locality over distance. And you might say, well, wait a second, if you can go backwards in time and have an effect, you could go back in time and kill your grandfather and never be born, so you have these causal paradoxes. But I think the answer to that is a quantum state can go backwards in time and have an effect on a system that hasn't collapsed yet, that hasn't collapsed. So once it's collapsed, it's a done deal. You couldn't go back and kill your grandfather because he's already, it's a done deal. He conceived your parents, and so forth and so on. So I don't think there's a problem with causal paradox. I wrote a paper about this called How Quantum Brain Biology Can Rescue Conscious Free Will, which deals with one aspect of the free will problem, which is this time problem. Now, it doesn't address determinism because even if that's true, you might say, well, you know, you were going to do that anyway, no matter what. And I recently engaged in a discussion about this, and the guy pinned me down on this, and because you can't rule out determinism, and I said it could be that our end result is going to be the same, but we can choose different paths, kind of like Feynman's path integral for an electron. And so we have free will kind of locally, but globally or in the long run, we don't. And I'll just stick with that. But I think you need quantum biology to have real-time conscious control. Whether that's true free will or not is another question.
Okay. Okay, so I guess that'll suffice as your statement on free will, and in referring to time travel, people may have gotten a sense for how weird some of this stuff can get, and we will return to this question of whether the conference you run has too much weird stuff. Well, I do want to turn to that, but first let's talk about these microtubules now, and the whole business of studying consciousness from the standpoint of anesthesiology, because well, I mean, as for the microtubules, you know, any theory that quantum effects in the brain give rise to consciousness runs into an argument by some people that actually, if you look at what it takes for quantum processes like this to take place, the brain wouldn't be a very hospitable environment. It needs to be colder than the brain or something or other. And you found, you've argued that microtubules, which are inside the neurons, are a place where you could have quantum effects. I think you see some evidence for that. And also, just as an anesthesiologist, you're in this interesting position of being in the business of eradicating consciousness, right? And that allows you to kind of observe what's going on in the brain when it is conscious and when it's not conscious. So, and that could give you some clue as to what you know, does give rise to consciousness. Do you want to talk a little about this paper that just came out in the journal Anesthesiology that I think you see as evidence in favor of your hypothesis that quantum effects could be going on in the brain, and it involves anesthesiology. And in fact, the journal had you write the editorial accompanying the paper. So do you want to talk about that?
Right. Maybe I should go back and introduce microtubules a little bit.
Oh, okay.
Because
maybe an introduction, you're right.
When I read Roger's book, he wrote it in 1989. I think I read it about 91. And at that point, I had been studying microtubules for about 20 years. In medical school, I did a research elective in a cancer lab and studying mitosis, how the chromosomes are pulled apart into identical pairs. And they're pulled apart once they replicate by structures called microtubules. And microtubules are cylindrical protein polymers made of a protein called tubulin. They're anchored by these structures called centrioles, which are also made of microtubules. And they grab each pair and pull them apart delicately. And if you don't have exact division of the chromosomes, you get too many over here, not enough over here, or some asymmetric division, you get abnormal mitosis, maldevelopment, possibly malignancy or developmental problems, or the cells just die. So most people in the lab at that time got obsessed with the genes, chromosomes. This is the dawn of the genetic engineering revolution. But for some reason, I got really interested in how these microtubules knew where to go and what to do, and how they organized or orchestrated this delicate dance of the chromosomes. They seemed to have some kind of intelligence and maybe even consciousness, I thought. Well, at that same time in the early 70s, a couple other things happened. The structure of microtubules was shown by crystallography to be a lattice polymer of individual proteins in a hexagonal lattice. And it was found that they're in neurons, in fact, in all cells, the fixative agent for electron microscopy had been dissolving them for 30 years. All of a sudden, they switch fixative and see all these microtubules, which they initially thought were artifact, but then they turned out to be real. And the third thing was that computers were new to me, at least. So I was trying to figure out how computers worked, and I was learning about Boolean switching matrices and automaton, that sort of thing. And so I got the idea that microtubules with this lattice structure might be computers in some sense, might be processing information, and that each tubulin in a microtubule could represent a state, a 1 or a 0, a yes or no, and that they interact with each other to process information. So I spent the next 20 years roughly studying microtubules and doing a lot of modeling of information processing in microtubules with physicists, including a guy at Los Alamos named Steen Rasmussen, where we modeled microtubule automata and showed that they could process information and even learn in simple networks. And I was going around a neural net and AI meetings saying, AI, people would say, as a singularity, say later, that, there's a 10 to the 11th, 100 billion neurons in a brain, roughly, 1,000 synapses, switching at about 100 hertz gives you 10 to the 16th operations per second. That's the calculation of AI. It goes back to the 80s, Hans Moravec, and then Kurzweil picked it up and so forth. And they were saying, well, as soon as we get to 10 to the 16th operations per second in a computer, we'll have brain equivalents and therefore consciousness, because obviously consciousness is a computation. What else could it be? Well, I don't think it is, but that's another story. So I was going around saying, no, that's not right. If you look inside the neurons, you have about 1 billion tubulins switching at about 10 megahertz, 10 million times. That's 10 to the 16th operations per second for every neuron. And then you have to multiply that times 10 to the 11th, 10 to the 27th operations per second. So I was saying, your goalpost is way, way, way downstream. You're not even close. So I became very unpopular in AI circles and somewhat of a pest. And they said, go away, you bother me. And, didn't bother, I didn't care. I was enjoying myself. But then one day somebody said, well, let's say you're right. You have all these operations. How does that explain consciousness? How does that explain love, joy, greenness, blue, pain, feelings, all that kind of? Basically, the hard problem was thrown at me before Dave invented the term. Although, as I said, other people had said it, and I had to realize that I realized at that time that this person was correct. That I was just a reductionist and had brought it to another level of reductionism. And it didn't really explain consciousness, even if it were true what I was saying. But fortunately, that same person, and unfortunately, I can't remember who it was, but suggested I read Roger's book, which I did.
Roger Penrose.
Roger Penrose's book, The Emperor's New Mind. And it was mind-blowing, really. And I didn't follow all the Gödel's argument. It got to be pretty dense philosophy and mathematics. And then the connection to quantum physics and space-time curvature and whatnot, I loved it. I thought it was so interesting. It seemed, pulling it out of left field and so forth. And when I asked Roger about it later, he said, well, he quoted Sherlock Holmes, or maybe he did it to someone else. When you eliminate the impossible, whatever's left must be correct, no matter how seemingly improbable. And in his mind, he had ruled out everything else. And because he needed something outside the system that was non-computable, and the only thing outside of a classical system is a quantum system, which required a solution to the measurement problem. So he came up with this idea of self-collapse, objective reduction, giving rise, and oh, by the way, it gave rise to consciousness and had these non-computable values. But he didn't have a candidate for a quantum system in the brain. Basically, he was describing a quantum computer where information can be in quantum bits or qubits of both 1 and 0 simultaneously. You reach threshold, and however, by whatever mechanism, the 1s and 0s collapse to 1 or 0 as the solution.
So was that, just to interject for a second, was that his argument, was that you're wrong that you can simulate the brain on the kind of computers you're using, but maybe you could simulate it on a quantum computer? Was that his view? That basically the brain is a quantum, has to at least have some quantum elements in it? Because now they actually are developing quantum computers, although they're in a primordial state. But is that the way he saw it?
To some extent. The problem with a quantum computer is that they run the quantum superpositions, and then they force the collapse by measuring the system, and that brings in randomness. Roger said, no, it has to self-collapse by this objective reduction mechanism. That's what gives you consciousness. And so he needed a quantum computer in the brain that would self-collapse by the subjective reduction and have some mechanism of interfacing with the nervous system to influence, cause neuronal firings, and regulate synapses, and interface with the brain as we know it. And there was a hint or suggestion that maybe superposition of neuron both firing and not firing could be a quantum computer, and so, or qubit or quantum bit. Although he didn't really say that because he realized that they were too large. So when I read this, I'm thinking, well, microtubules are what he needs, because the states of each tubulin are regulated by these quantum states in the pi resonance orbitals and aromatic amino acids inside the protein.
Now, is that an agreed upon fact that they are regulated by quantum states, or that's your theory?
That was our theory then. There's now evidence for it. But at least we were getting down to the level where quantum effects could become important and relevant. And still, we were, when we eventually published our theory of microtubule quantum computing influencing neuronal states and collapsing by objective reduction, people said that's impossible, because to build a quantum computer in the lab, you have to, you're plagued by this decoherence. Any thermal vibration will destroy the quantum state. Therefore, you need to do it at absolute zero temperature. The brain's at 37.6 degrees centigrade. That's way too, as they said, warm, wet, and noisy for a quantum system. Mm-hmm. And so, we were obviously crazy, they said. However, well, at that point, we came up with some arguments on how microtubules could avoid decoherence. And going back to Froelich, who said these quantum vibrations actually were a quantum state in microtubules or in proteins in general, and came up with some arguments and basically saying, look, biology's had billions of years to figure this out. It'd be evolutionarily advantageous to have quantum systems. So the biology figured it out. We don't know how yet. Anyway, still, we were ridiculed and thought to be crazy. And then in about 2006, it was discovered that plants use quantum coherence in sunlight, obviously warm, to generate food. The plant.
And is there a thumbnail definition of what quantum coherence? Do you mean they collapse the wave function, or what? Or what?
Quantum, in this sense, it's almost equivalent to superposition, because what happens is the plant collects photons in one part of this complex. The photons are converted to electronic excitations called excitons, which are quantum particles, which then go through another protein to the reaction center, where they're converted to chemical energy and made into food. Mm-hmm. Now, when they go through this intermediary protein, it's called the FMO protein, and this was discovered in 2006 or so. The excitons go through 7 pi resonance chromophores, they're called, simultaneously. So the energy goes through all possible pathways simultaneously to optimize efficiency to get to the target to make food. And if this energy transfer wasn't very, very, very efficient, the plant wouldn't be able to make food efficiently. Animals couldn't eat the food. We couldn't eat the plants or the animals. And life on Earth may not.
So the energy is using quantum properties to travel via more than one path at once, so to speak. Is that it?
Yes. Yes. Superposition of all possible pathways. Mm-hmm. Highly efficient.
Yeah, I wish I could do it.
Yeah.
So, okay. So there's that evidence. Now this, and I know there's other evidence, but this paper that just came out in the journal Anesthesiology is interesting. I think I kind of tell me if I understand it. So there's this gas that does induce anesthesia, right? It's like xenon. What is it?
Xenon. It's an anesthetic. Let me back up a little bit about anesthesia, because I also started studying anesthetic mechanisms when I went into anesthesiology in 1975. I was really interested in consciousness. At first, I didn't see any. There was some connection between anesthesia and microtubules, because excessive anesthesia caused microtubules to depolymerize. So there was one theory that anesthesia worked by depolymerizing microtubules. That turned out to be wrong, because it takes about 5 times as much anesthesia to depolymerize microtubules as it does to cause anesthesia. Everybody in the field, in 1984, it was shown that anesthetics act in proteins in these pi resonance orbitals of aromatic amino acids. Pi resonance is like benzene, where you have a hexagonal ring or a hexagon and a pentagon with electrons that are delocalized. So you have an electron cloud. So you have this this quantum state, this delocalized electron cloud inside every protein. And we know that anesthesia acts in this environment. And we know that from studies at the turn of the 20th century by two guys, Meyer and Overton, working separately in England and Germany, who so let me back up even further. In the 1800s, it was discovered that there were a bunch of gases that if you breathe them, or if an animal breathed them, they would become unresponsive and roll over, and if as long as they kept on breathing, they would come back and be perfectly fine. And
so a whole bunch of like chloroform, or what was like the first?
Chloroform, diethyl ether,
yeah,
nitrous oxide. And nitrous oxide and ether in particular, at low doses, caused euphoria, and they were used for recreation. Ether frolic.
So they had found a way to eliminate consciousness without killing the animal, which is significant.
Right, as long as you give too much, and as long as they kept on breathing, they don't obstruct and so forth. But the point was that these gases, which caused anesthesia, had various different types of chemical structures. It wasn't like they all had almost the same chemical structure. You had ethers, you had halogenated hydrocarbons, you had nitrous oxide, you had xenon, an inert element, single atom. What they had in common was completed electron outer shells. So they were nonpolar. So when you have a complete electron outer shell, let's say with 8 electrons, they're all happy. There's no charge. They're nonpolar, and it's kind of like oil and water. Oil and water don't mix. So these
which is the oil and which is the water? So you mean the gases don't interact particularly with a lot of stuff, or what? What do you mean? We're talking about the gases that induce anesthesia, and you're saying they have in common something about a complete outer electron shell or something, and that makes them highly kind of stable and non-interactive.
Yes, and soluble in oil, in olive oil in particular.
Literally oil. So it's literally an oil and almost thing. Okay, so they don't dissolve in oil.
They do dissolve in oil.
They do dissolve in oil. Okay.
They don't dissolve in water. They're very poorly soluble in water or blood. Okay. So now most other pharmacology, biochemistry is dealing with the charges, polar charges, which are there on the surface of the protein, but if you go inside the protein, you have this oil-like pocket of aromatic amino acid rings.
Okay, I think we may have lost some people. So, what is the kind of takeaway? So we've got these gases. I mean, how does this relate to your belief that quantum effects happen in the brain and are, I guess, influenced via anesthesia?
Let me. I don't want to lose people. Let me back up one second. What Meyer and Overton did was plot the potency of a bunch of different gases versus their solubility in olive oil, and got a perfectly straight line over many, many orders of magnitude. The more soluble in olive oil, the more potent, and the less you needed to cause anesthesia. Now, why that was remains a mystery. However, it turns out that this oil-like environment is quantum friendly. That's where quantum stuff happens in these pi resonance.
So the more unstable, the more conducive they are to anesthesia in a certain sense? Or is that not the right term?
The more soluble in olive oil, the more potent they are.
The more amenable they are to being broken down.
No, they're not broken down at all.
Oh,
they're not. There's no chemical reaction. There's they don't have any chemical reactions.
Okay. So we still don't know exactly what it means that the more soluble in oil, the more potent anesthetically.
Nobody knew that until recently. It remained a mystery, and in fact, people working in anesthesia tried to get rid of that, despite this amazing correlation, because they couldn't explain it. And what we've done in the last few years is realize that this oil-like environment. Now, when you say oil, you think of benzene or gas or olive oil, which is just a bunch of these mixed together. But this is not quite that. This is more like a benzene ring with next to at a critical distance to the next one and the next one. It's kind of like graphene. Graphene is a quantum material, which is basically ribbons of these pi resonance groups. Mm-hmm. So they're quantum friendly. They can have quantum effects that aren't disrupted by heat, that aren't disrupted by water, wetness, noise, because they oscillate coherently. So the more potent in olive oil, the more they get into this quantum-friendly region inside critical brain proteins necessary for consciousness, and then take away the consciousness. And then when you pull the gas away, the quantum vibrations resume, and the patient wakes up.
So it's your interpretation that the reason the more potent anesthetics are more soluble in oil is because they are also more likely to kind of get involved in quantum effects in the brain?
They impair quantum effects.
Get involved in the sense of neutralizing quantum effects, because the quantum effects are the source of the consciousness, in your view.
Correct.
Which brings us to this paper in anesthesia, in the journal Anesthesiology, which is just out, which I think is consistent with this scenario, right?
Yes, and I'll come to that in a second. But let me back up one second. Last summer, my colleagues and I published a paper where we on a supercomputer, I didn't do it, my friends did it, modeled all these pi resonance oscillations in tubulin. There's 86 aromatic amino acids. And you run it on a supercomputer and look at the oscillations of these pi resonance, these quantum oscillations, quantum vibrations. And you get a spectrum around with a common mode peak at about 613 terahertz. Now that's blue light in a visible spectrum. But that doesn't mean we're emanating blue light because it stays within the system. But there's this peak at 613 terahertz. They then, in the simulation, added 8 different anesthetic molecules and 2 gases which follow Meyer-Overton but don't cause anesthesia. And what we found was that all the anesthetics abolished the 613 terahertz peak and shifted it much slower. The non-anesthetics, which bind there but don't cause anesthesia, did not shift it. Therefore, this 613 terahertz blue light peak correlates with consciousness, and getting rid of it correlates with anesthesia. So that was our paper last summer.
So so there's a certain frequency of light that effective anesthetic gases do what with? What is the nature of their relationship?
They dampen it. They make it dampen it.
So there's some kind of interaction at a certain frequency of light that's going on between it when the anesthetics are effective. They interact with the light at that frequency in some significant way, and well, you're looking displeased, like I said.
I would say they interact with the light. They dampen the quantum oscillations which give rise to the light, or cause the emission of that blue light spectrum. So the oscillations are generating the blue light. You dampen the oscillation, no blue light.
So these are like manifestly quantum effects. There's not controversy over that, or
no, they're definitely quantum effects.
Okay. Okay. So does that bring us to this most recent paper?
Yes. In a roundabout way. So about the same time, about 6 months ago, I got a request from Anesthesiology, the preeminent journal in our field, to review a paper from China, which had taken xenon, which is one of these anesthetics, and made a bunch of isotopes for xenon. Now, xenon has I forget now, 13, I forget how many atoms, how many protons, whatever the atomic weight is, and then a various number of neutrons. And some of these protons, it's all xenon, but the different number of neutrons gives you different isotopes. And some of these isotopes result in a nuclear spin, which means that it's a quantum property of the nucleus of the xenon, or the xenon as a whole, which has a nuclear spin. Now, nuclear spin is a quantum property, but again, nobody really understands it. It has an angular momentum, it has a torque, it has a directionality. Most significantly, it's good for entanglement. If you have a nuclear spin over here and a nuclear spin over here, they can communicate non-locally. This can be
just to pause on that. You don't. Whatever spin is, think of it as like as the particle can be heads or tails. Just imagine that that's what we mean when we say the spin can be this or that. And there's like a law that two particles which are initially intertwined in some way, even once separated, their spins have to be complementary, I guess, so that if one is heads, the other one has to be tails. And
right.
and entanglement is this finding which Einstein saw as an implication of quantum physics and rejected, but these days quantum physicists are pretty confident that it's the case, that if you measure a particle right here, that the act of measurement, by forcing the spin to assume a definite state, instantaneously influences the other particle that's far away, which means it influences in some sense traveling faster than the speed of light. So that's that footnote on entanglement. And that is where you often hear this property called spin is in the context of people explaining entanglement. So,
right.
so
Einstein didn't like entanglement because, as I said, it implied faster than light, which he said was, an absolute. And by the way, Roger Penrose is the only one I've ever seen explain that at a meeting of the World Society on Quantum Information in 1998, where he got up and drew the famous Einstein-Podolsky-Rosen experiment. Einstein-Podolsky-Rosen published this experiment, a thought experiment in the 30s, I think, that was intended to disprove entanglement. Because if you have two complementary particles in a superposition and you send one of them over here and one of them over here, if you make a measurement here, this one instantly reacts. Now, what Roger said was, if you make a measurement here, the quantum information goes backward in time to when they were together, and then forward in time to this one, so that it's not really faster than light. It's just going backwards in time. So that kind of gets.
I'm not sure which of those scenarios I consider weirder, but okay. So there is, in any event, physicists think entanglement happens. There's this property called spin, and that brings us back to this paper in the journal Anesthesiology, because that turned out to be a key variable, right, as far as whether the xenon, there were two versions of this xenon gas that in terms of conventional chemical interaction have identical properties. So if we're just talking conventional chemistry, they should be equally effective in inducing anesthesia. But they had different quantum properties in terms of this spin thing, and they were not equally effective in inducing anesthesia, right?
The isotope that had nuclear spin 1/2, which is the most potent nuclear spin, was 50% less potent than xenon without the nuclear spin. And they calculated the polarizability to see if the spin was affecting the electron clouds, which is what ultimately causes anesthesia, and they didn't. The polarizability was the same. So they argued that the nuclear spin was somehow directly promoting consciousness, and that consciousness must involve quantum states, and referenced our work and some other people who've been arguing this along the way. And so I was asked to review the paper, and I like the argument, of course. I liked the whole paper, and I thought it was very well conceived, very well written. And there were 4 reviewers. We argued back and forth a long time, and eventually it was accepted, and they asked me to write the editorial to explain how in the world nuclear spin can affect consciousness. And I said it could very well be by entanglement, because you're just adding more entanglement to the whole brain system that antagonizes the anesthetic effect. And as an analogy, I said, imagine these spins and entanglement are kind of like our quantum Wi-Fi, I called it. So imagine you have a Wi-Fi system in a building or your house, and your Wi-Fi is not working. You add another router, or you add a couple of routers, and service improves. So the more routers, the more quantum spin you have in the brain, the more entanglement you have. Now, how could this affect brain function as we know it? Well, I gave the following example. It's called the binding problem in neuroscience. This is something the neuroscientists have a big problem with. For example, if you look at an object moving in the sky, its shape, color, motion, and meaning are processed at different times, different locations of visual cortex. Mm-hmm. So V1, V2, V3, V4, shape, color, motion, meaning. But if you look at something in the sky, you don't see a diamond shape, you don't see red, you don't see fluttering. You say, oh, it's a kite. You don't see that sequentially. You just say, oh, it's a red kite. So that's all bound together. Now, Samir Zeki years ago had this idea of because he observed that these different processes, shape, color, motion, meaning, were different places, different times. And he called these micro-consciousnesses, and how they're all bound together in a unified conscious percept is the question. Well, if you have entanglement due to spins, you don't have xenon in the brain, but we have other sources of spin. They could entangle all this, so you don't see this sequentially, even in different parts of the brain. You see it instantaneously, simultaneously, in one conscious percept. So that was one way that more entanglement could promote consciousness, by promoting binding and basically hooking things up together through quantum entanglement more readily.
Okay, and in any event, at a slightly less elaborate level of interpretation, the idea is that the reason the one version of the xenon gas does not as effectively anesthetize is because
I mean, its chemistry is having the anesthetic effect, but then
Right.
the quantum effects it's inducing are boosting consciousness so that you don't wind up on balance eliminating consciousness as thoroughly as the chemically identical version of the gas, the chemically identical but different in quantum terms version of the gas.
Yes, that's right.
That's a fascinating finding. So that's good.
Yeah.
Now, why don't we turn to the other thing that came out, maybe at roughly the same time, but this piece I alluded to in, what is it, the Journal of Higher Education? Is that the...
Chronicles of Higher Education.
Chronicle of Higher Education, right. It's a, it's a well-known thing. And this, I guess a staff writer for the Chronicle went to your annual conference just took place. He went there, he visited, and his argument, or he talked to people whose argument is that you have too much like woo stuff at the conference, and that you're doing damage to the field of consciousness studies. And I know, to some extent you're unabashed about that. I mean, you're aware that, when you bring Deepak Chopra to a conference, you're inviting a certain kind of blowback. And also, I know you are not dismissive of the so-called paranormal researchers the way other people are. And so I want to talk about what we mean by paranormal. But there was an interesting quote from you in this piece. The journalist says, I asked Hameroff about this one evening. In other words, is there too much woo? And this is what he said, and this is the quote from you. The scientists who poo-poo the mystical stuff can't explain the hard problem. I think that's true. I mean, in fairness, as I think he goes on to point out, nobody else can either, right? I mean, or do you think that, before we get into the woo stuff, do you think that your quantum explanation is in principle, that is an explanation of the hard problem, if it's borne out?
I think it's closer than anybody has ever come.
Okay. So now on to the woo stuff. Which I know you take seriously, things like, and I guess we alluded to this a little, but, well, no, we didn't. But I think you do take seriously the possibility of precognition as a version of backwards time travel.
Yes.
Is that right?
There's good evidence for that, actually. But people dismiss it. Well, it's just parapsychology. But I've heard a lot of talks by parapsychologists, and their statistics and their methodology is more rigorous than most scientists. Daryl Bem, we had him in 2012. He did 9 experiments. 8 of 9 showed precognitive effects. Bierman and Radin have been showing this for years. Other people have shown it. People show it accidentally. We had a guy from Christoph Koch's lab give a talk a few years ago where they had electrodes inside the brain of humans for seizure mapping, and while they were waiting to have a seizure, they did these studies where they showed them these pictures of faces, and they would find that certain neurons would fire to certain faces, the Halle Berry neuron or the Bill Clinton neuron, and so forth. So he was showing the faces on the screen, on the same screen, the neuron fire activity like that. And it seemed to me that in the audience that the neuron was firing slightly before the picture came up. So I asked him. I said exactly that. It seemed to me that the neuron was firing slightly before the picture came up. Are they synchronized? Is that really what's happening? He said, yeah, that's synchronized. That's what really happened. Now, and I said, how do you explain that? He said, I can't explain it. And I invited him for the next year's conference to talk about it. And he came and he talked about something else. And he said Christoph told him not to talk about that. It would ruin his career. So I think there's a cover-up in neuroscience about this precognitive effect.
Now what the standard thing that mainstream psychologists say about paranormal researchers is that their stuff does not replicate well. But I don't know if that's true. It's what they say.
Well, I don't try to replicate it, but I think there's enough of it that you have to take it seriously. And I've had enough anomalous experiences in my own life to suspect that something like that is true. Yeah. And if there's quantum biology going on, there's no reason why it isn't true. There couldn't be entanglement across distance.
So what's an example of a kind of anomalous experience
that I've had?
Yeah.
Precognition. I kind of have a sense of what somebody's going to say or what's going to happen. Just a fraction of a second before it happens. Mm-hmm. I think a lot of people do. You probably do too.
Oh, I've had things like that. The problem is that a certain number of these things are going to happen randomly. It's like weird coincidences. It's like some number of weird coincidences are just going to happen, and it's very hard to do the math rigorously, because the world is so complicated, so that you can say, well, are weird coincidences happening more than what randomness would predict? And also, we know that chemicals can affect the perception of these things. So if you give somebody like marijuana or maybe a psychedelic, they're more likely to see coincidences as meaningful, and then the person sitting next to them who's not high is not going, whoa, So, and I'm not even judging which one is right and which one's wrong. It's just that we know that sensitivity to coincidences is a biochemically influenceable thing. And who knows whether our normal state of biochemistry is good at judging what's, I'm not dismissing it. I'm just saying it's so.
I'd say quantum chemistry, quantum physics at a level below biochemistry.
Well, that would be your argument, yeah.
Let me back up.
That would be your argument for why the stuff really happens. What I'm saying is that we know that just conventional chemicals like THC can make a person more prone to see two events as an unusual coincidence than they would have been if they hadn't smoked the marijuana. That's just an observed fact. So I'm just making the point that it's hard to know whether to trust your intuition that coincidences are really weird or are just happening at the frequency that randomness would predict. That's the only point I'm making.
Well, let me respond to that. In the editorial, I had two illustration of a hierarchy going from cortex to neuron to microtubule to tubulin down to the pi resonance oscillations. 6 levels based on experimental results from Anirban Bandyopadhyay of quantum effects in microtubules. And basically what I've suggested, not so much in that article but elsewhere, is that the brain isn't so much a computer as it is an orchestra. It's more like music. In fact, consciousness is more like music than it is the output of a computation. Because if you have the output of a computation, who's looking at the results? If you have music, the music just is, except it has some intrinsic experiential aspect. So in this hierarchy, and ORCOR in our objective reduction,
orchestrated objective reduction is the term.
Right, that's the theory.
Now, is orchestrated a reference to music in that?
To some extent. Mm-hmm. Actually, so when we were naming our theory in 1994, Roger and I were in Denmark, and we were staying in a house together for a couple of weeks, and we were developing this model, and we had the idea that the microtubules would organize the quantum information to give it meaning and cognition and so forth. And we wondered what to call it. And I came up with the idea of, and I harkened back to my ideas of how the microtubule spindles were orchestrating the cell division. I said, how about orchestrated objective reduction? And he immediately liked it. And in fact, he said, I was thinking about that for objective reduction because it's orchestrated by the Platonic values. And he kind of regretted not calling objective reduction orchestrated reduction. So orchestrated objective reduction basically means that all the micro-consciousness, the proto-consciousness that would be occurring everywhere are organized and put into unified conscious percepts. The metaphor analogy would be the following. If you go to a symphony and the orchestra is warming up and every musician is playing his or her instrument, tuning it, and you hear all these noises, tones, and it's not music. It's a cacophony of sounds and noises. That's not music. That'd be like the proto-consciousness occurring everywhere, here and there. Then they start playing Mozart or Brahms or Beethoven or whatever. It's orchestrated the same way the microtubule quantum vibrations orchestrate the quantum information and the proto-conscious events into full, rich conscious experience.
And that's when you have full conscious experience. So when you say orchestrated by the Platonic values, is Penrose saying that, again, I don't know how to conceive of these Platonic values, but he's saying that the Platonic ideals or something, the Platonic forms or something, are orchestrating consciousness.
No, actually, it's more like the microtubules are orchestrating the quantum computation, the quantum information, because they're doing the organization of the orchestration. And then when collapse occurs, this is the way I look at it anyway. When collapse occurs, the Platonic values kick in and push the results one way or the other, like a bias. But the orchestration is what leads up to the moment of collapse.
So the microtubules kind of set up the table, so to speak. They set up the system so that it's ready to collapse, and the question of which way it collapses, you know, whether the electron is here or there or whatever, that is determined by the Platonic values.
Right. They set up probabilities, and then there's a last ditch influence by the Platonic values. If things are up in the air, it's going to tend to go to, in my view, what resonates with the Platonic values in the universe.
I know you can't speak for Penrose, but do you know, I mean, and I should try to have a conversation with him myself, but do you know if he views this almost as a religion? I mean, you know, Platonic, you know, I mean, for Plato, that did have like divine, you know, it's like there was the realm of forms was like a kind of, I think, divine realm. But the way you're judging by the expression on your face, the answer is no. So never mind.
Well, you know, that's exactly what I thought. That this is spiritual. This is like, you know, following the way of the Tao, divine guidance, whatever you want to call it. And when I asked him that many years ago, he said, "I just don't find that useful to consider that." Uh-huh. So I wouldn't say that he says no. He just doesn't want to go there.
Okay. So now back to the other things that might be considered wooish by some people. This paranormal thing. One question is, you know, the term is paranormal, but I sense that you think that actually if the explanation for phenomena we call paranormal, when it is found, assuming the phenomena are real, they will be within the bounds of science. I mean, an example for me has always been like people, like if you said, oh, you know, he can read minds, people would go, whoa, no, that's impossible. And I'd say, well, actually, I mean, in principle, we know that brains emit waves. It's not impossible that one person's brain could be capable of perceiving the physical waves, you know, through a quirk of evolution or whatever, in which case it would be a sensory apparatus for perceiving physical waves. It would be a sixth sense in the sense of being a literal sense, another sense organ, right? So you can imagine that things that we call paranormal, you can imagine explanations for them that would be within the realm of science, and it wouldn't be so weird. Is your view that every paranormal phenomenon you would take seriously, ultimately, if it's real, it would be explained within the bounds of science?
Yes, by quantum entanglement. You know, what you said before about waves, electromagnetic waves don't do it because they fall off so drastically with distance. Thermal radiation, they all get washed out by randomization and so forth. I think only entanglement really can explain it. So I don't think electromagnetic...
Explain what in this case? Which paranormal phenomenon?
Well, precognition, backward time effects, parapsychology, connection over distance, how people can sense things over distance.
Like sense what's happening with some other person they know or something?
Yeah, having a feeling that something happened to your friend or a loved one or something like that who's nowhere around. And, you know, I've experienced that. You know, we just have this sixth sense. And I think that has to be quantum entanglement. It doesn't appear to be depend on proximity. It could be fairly far away. So, yeah, I think, now I'm not saying all claims of paranormal are correct. They could be fake. And some of them could be wrong. But I think a lot of them are right. And I think they're perfectly within the bounds of science and physics with quantum entanglement. You know, the problem is the problem has always been, well, how do you have quantum effects in the warm, wet, noisy brain? And I think we've solved that with Honor-Bond's experiments in microtubules and other things. So you know, it doesn't matter that it's warm, wet, noisy, because the warm means the energy is pumping coherence, which actually so it's not really noisy. It's organized and coherent, and it's not really wet because you're in the nonpolar oil-like regions. So I think quantum brain biology is going to turn out to be more and more important as we learn more about it.
Okay, and so when if you're asked to justify including what critics would call the woo crowd, I mean, we should say that your conference has over the years featured all the big names in mainstream consciousness studies. You know, Dan Dennett, David Chalmers, and so on. and it continues to have these people attend. But you do have, Deepak Chopra, and Deepak Chopra. I mean, you could argue that, leaving aside whatever claims he may have made about cures of maladies and so on, his view of consciousness, as I understand it, is a kind of an Eastern view that's actually taken somewhat seriously in philosophical circles, according to which consciousness is in some sense more fundamental than the physical world. It's hard to wrap your mind around, but that leads me to the question is like your defense of having all these people that hey, consciousness is so weird. We are so far, from having an obvious consensus acceptable explanation, and in fact, it's not so clear. To me, it's not so clear we can have one, honestly. I mean, by virtue of the nature of the problem. But anyway, is your defense is that, look, this is just different from conventional problems in science. It is so weird that you have to open the playing field up to all kinds of players who are not your regular players. Is that kind of your defense?
To some extent. First of all, about Deepak, yeah, he does follow Vedanta, which is that consciousness is everything, and we're all manifestation of a big consciousness. Now, that's no different whatsoever than Bishop Berkeley, who was an idealist. It's exactly what Bishop Berkeley said. So why is that so woo compared to Bishop? Is Bishop Berkeley woo?
Right. Bishop Berkeley is a Western philosopher who's taught in standard intro philosophy courses, and idealism is not casually dismissed. Idealism is the term for his view that the physical world is not what it seems to be, and that consciousness is more fundamental.
So how is Deepak's view any different? It's not.
Okay, but and then who are the other people that complain about? I mean, you mentioned that you've had people like Daryl Bem, I guess, and so-called parapsychologists or paranormal researchers. That's the main complaint.
Well, let me say that regarding the article, you got to understand that the conference is a week long. There are 40-some plenary talks, plenary meaning one speaker at a time, big audience. In the evening, we break into parallel sessions, 9 separate rooms, and then posters, and then exhibits. Now, admittedly, some of the posters and some of the concurrent talks are not as rigorous as the plenaries. I didn't hear any complaint outside of Deepak. I didn't hear any complaint from that article about any speaker except for Deepak. And I thought Deepak's talk was relevant. It was in a session on panpsychism, idealism, panpsychism, and pan-protopsychism. And I thought, that was an excellent session. But other than that, all the other, I didn't hear any complaints about the plenary speakers, except maybe Dave Chalmers complained about too much microtubule stuff. But as it turns out, at least in my view, that's where the interesting stuff is happening now. Travis Craddock gave a great talk about how anesthesia seems to act on microtubules, which goes against the mainstream in anesthetic mechanism research. And the other 3 speakers in that session had different views, one on GABA receptors, one on NMDA receptors, one on some other receptor, and then Travis on microtubules. So I thought that was a very fair session. And I think, to me, I'm biased, obviously, but Travis's results were far more convincing than the others. So he was the only one that showed a correlation with Meyer-Overton. So I really think we're going to win that battle in terms of anesthesia selectively. And I say selectively because the anesthetized brain is still quite active electrically, selectively blocking consciousness while sparing non-conscious activities. So, yeah, that was a microtubule talk, and Anirban talked a little bit about microtubules. But those were like that 3 out of 40. We had a lot of neuroscience that didn't even get mentioned in that article. We had some really good physics. We had language. We had technology, robotics, AI, and so forth. So, as I admitted, there is a soft underbelly on the posters and so forth that aren't as rigorous, but that he seemed to dwell on that and ignore the great stuff that was happening in the plenary session. So I think he kind of missed the boat.
Well, it's definitely true. The poster sessions can be a hit. I mean, the poster, like I remember I used to go to these Human Behavior and Evolution Society meetings when I was writing a book on evolutionary psychology, and you go to the poster area. These are people who are not even making presentations, but they are permitted to put a theory on. And, you definitely had some crackpot theories.
And there's a bar. And I was drinking when he interviewed me, which is probably a mistake.
Okay, so anything in particular you want to retract, or you just want to vow to not drink next time you talk to him?
I don't know. I don't want to get in the business of retracting, but I was a little bit dismissive. I was tired when he talked to me, and he kind of attacked me right off the bat, and I got defensive, which was a mistake. But suffice to say that I will stand by the plenary session and plenary sessions, which I think is I think when it comes to approaching the hard problem, the science of consciousness, I think our plenary sessions are miles ahead of any other conference. The ASSC, that was the Association of the Scientific Study of Consciousness, which grew out of our conference back in '96 because they wanted it to be more, because we had stuff on parapsychology, we had stuff on quantum, and they wanted to, be okay in their academic environment. So they got rid of all that, formed their own society. And I've been to their meetings a couple times, and I said in the article, they're boring and they're very reductionist, and I don't think they really address consciousness. They talk about where it might be happening. They assume this neuron equals bit computational view, which I think is wrong. I mean, the brain, and I made a derogatory comment about brain mappers, which the writer took me to task for. But, we're spending billions, if not trillions, on mapping the human brain, where they take this fixative agent and so that you can see every neuron, the surface of the membrane, and they're dissolving everything inside. And so they're assuming right from the start that nothing inside the neuron matters, that it's just a big map. And, I would bet everything I got that that's not going to explain consciousness in any way. That, they say, well, we'll find the right circuit, we'll find the right this. I say, BS, show me. For example, there's a worm, C. elegans, whose nervous system has been mapped entirely for about 15 years. Every neuron, every synapse is known. They've mapped it, they simulated it, they made an artificial worm, they turned it on, and nothing happens. It just sits there. I'm not saying it should be conscious. I'm saying it should maybe swim around like a worm. It just sits there, doesn't do anything. So if that's the case, what do they expect to get out of mapping the 100 billion neurons in the brain without going to a deeper level?
And you think the deeper level would take them inside the neuron and would include things
the
microtubules
like and eventually the quantum processes, yes.
Yeah.
And eventually to space-time geometry, but that's, a ways off at least.
Okay. Well, thank you for taking the time, Stuart. We'll link to all the things we've talked about, including this article, including the editorial you wrote for Anesthesiology, and I guess the article itself. Is there anything else you want us to link to, or anywhere else you would direct people?
You might say, okay, what good is all this? And outside of understanding and so forth. And one of the projects I've become involved in the last it's been 6 years now is when Honorbaum discovered that microtubules have these quantum resonances in terahertz, gigahertz, megahertz, kilohertz. It occurred to me that, and people are doing brain stimulation, transcranial magnetic stimulation, right, transcranial electrical stimulation, photons. And I said, maybe we could use one of these frequency ranges to address microtubules to alter consciousness or treat mental and cognitive disorders. And so megahertz intrigued me because in electromagnetic waves, it's radio frequency. So I'm not interested in putting radio waves into the brain. But in mechanical vibrations, it's ultrasound. And we use ultrasound in medicine all the time. We have for 100 years to image. It goes ultrasound, mechanical vibrations in megahertz, goes through tissues and then reflects off surfaces. So you get an image of the internal part of the body. And you can see babies in the uterus moving around, and you can see organs. And we use it all the time. People come to the emergency room. First thing they do is something in the belly, ultrasound the belly, and see what's going on. And it's actually approved for brain imaging too. Although this is when CT and MRI came along, it wasn't needed, but it's still approved and used for imaging the brain in newborns through the fontanelle where there's no skull. Mm-hmm. And so I said, well, it can't be that harmful. And I wondered if anybody had tried putting ultrasound into the brain to see physiological or cognitive or some kind of mental effects. And sure enough, a guy at Arizona State University, our arch rival up the freeway, had been doing a guy named Jamie Tyler, a really excellent researcher, had been studying at that time. This is 2012, had been studying ultrasound into animals, and he'd implant electrodes and then do them with ultrasound. He'd see electrical activity. He could hit the motor cortex here and make this paw move, that sort of thing. So it's having some physiological effect. This is at low doses. If you give high doses, it causes heating. It can actually cause destruction. But if you're careful and reasonable in terms of the intensity and the duration, it's harmless. So I told my colleagues in anesthesia, I said, we should try this on our chronic pain patients because they're depressed. Maybe they'll feel better. And they said, yeah, right. This was your idea. You got a shaved head. You try it first. So they goaded me into trying it. And I thought about it. I said, well, babies, newborns have it. It can't be that bad. So at the end of one day, they're all sitting around a table watching me, and they kind of dared me. So I took our ultrasound machine, which we have in the OR. We use it for nerve blocks and whatnot, and put some gel on it, put it up to my head, and turned it on for about 15, 20 seconds. I didn't feel a thing, so I put it down. I said, well, that's too bad. I thought it might do something. And about a minute later, I got a buzz, and I felt actually energized and enthused and interested, and it lasted for about an hour. And I said, yeah, we should try this. So we did the first study on depression in pain patients and published in Brain Stimulation in 2013. And since then, there's been a lot of that was the first human study on mental states. And Tyler congratulated me. You did the first one. So since then, there's been a lot of human studies. And I've been working with a colleague named Jay Sanguinetti, who has developed a method to put ultrasound at depth. So he could focus it at any particular part. And of these other modalities, only ultrasound can be targeted, can be focused at a particular brain areas. Everything else fans out. Mm-hmm. So, and he can focus it at depth. So and we did a pilot study in Alzheimer's. Now, in Alzheimer's disease, your microtubules fall apart. And yes, there's the amyloid plaques, but the real damage is the microtubules disassemble. So we know from Honorbound's work that 2 megahertz promotes microtubule assembly. So we did a pilot study in dementia patients and found encouraging positive results. And we want, anecdotally by caretakers, they were more interested. And
well,
so
are you going to do a controlled study on that?
Yes, we intend to. We needed a better device, and now we have Jay's device, and we're going to do that. And he's found something else that's very interesting. He's working with a well-known meditator named Shinzen Yang, who's written a lot about.
I know Shinzen Yang. He's been on Meaning of Life TV.
Okay, so Shinzen Yang has mastered this meditative technique for Buddhist non-attachment, where basically the way I look at it, you're just totally in the moment. There's no mind wandering. There's no obsession. There's no worrying. You're just here and now, and nothing else matters. And to him, that's a blissful state. Right. And he decided that I don't know how he figured this out. He's apparently a neuroscientist too, or knows a lot of neuroscience. That it was the head of the caudate of all things that was active when in this state. And maybe he had functional MRIs when he was in the state. I'm not sure. Anyway, so Jay develops a technique to ultrasound the head of the caudate and found that he could reproduce this non-attachment state in Shinzen and in other people. So we're attempting to launch studies at the University of Arizona with this device for meditative state, which could be good for anxiety, OCD, addiction even, because pain and addiction, a lot of that component is due to worrying and obsessing and so forth. Mm-hmm. So we intend to try for that, as well as for Alzheimer's and brain injury, because we may be promoting activity in the microtubules to regrow synapses and to reassemble and actually repair mechanisms. So we hope it'll be useful for mental and cognitive disorders.
Okay. Well, we will. Some of what you just described sounds like there are papers about it, and we'll try to find those and link to those. And some of it sounds like work in progress. But if there's anything else you want us to link to, just email it to me. Okay. And thank you so much again for taking the time. It's fascinating stuff, and we will stay tuned.
Thank you.
Okay. Bye-bye.